Previously, we discussed the free response characteristics in the first order DC circuits, where the transients were initiated by the initial conditions only. In this particular, we are going to discuss the step response, where the transients are initiated because of the external DC source. So, as a recap, we have gone through the properties of the RLC elements. The VI relationship suggests there is no time dependency for the resistance, whereas there is a time dependency in case of inductor and the capacitor. Further, in case of capacitor, the voltage cannot be changed instantaneously, which suggests that the voltage must be continuous across the capacitor. This continuity is explained by the relationship Vc 0 minus is equal to Vc 0 plus. So, this 0 is having a reference of the switch operation, or the condition basically is translated as the capacitor voltage before the switch operation must be exactly equal to the capacitor voltage after the switch operation. Further, the capacitor voltage, when say fully charged with the DC, it behaves like a open circuit. In case of inductor, the current cannot be changed instantaneously, and the continuity of the inductor current is suggested by the condition IL0 minus is equal to IL0 plus. When say the DC current is applied for sufficient long time, inductor behaves as short circuit. So, recap that the transients situation is arising when say the circuit is having energy storage elements, when say there is a switching operations. Because of this, there is a change in the operating conditions. Because of the time dependency nature, the equations are coming out to be dynamic in nature, where we have to deal with the differential equation instead of the algebraic equations as far as the KCL KVL are concerned. And as mentioned previously, that the response is having two components, transient and the steady state component. Transient response are temporary in nature. They are expected to be decay with time and ultimately vanish for a stable system. In the free response characteristic which we discussed for the RC and the RL circuits, here say how the capacitor got initially charged, or how there is a current initially in the inductor, that particular is not shown. So, immediately after the switching operation, there is no external source, and the transients are ultimately established or driven by the initial charge on the capacitor or initial current on the inductor. These particular behavior are explained by the respective relation V is equal to V0 e to the power minus t upon tau, I is equal to I0 e to the power minus t upon tau. This tau, which is the time constant, it is depending on the circuit parameters, so which is RC for the capacitive circuits and L upon R for the inductive circuits. So, this particular time constant is also suggesting the physical characteristics of the system. Sizes of two components, transients and the steady state response. The transient response is also regarded as the natural response, which is decaying continuously and expected to vanish completely with the progress of time for a stable system, where say the forced or the steady state response is due to the external source. Previously, we have discussed the free response characteristics. So, this response is only established by the initially charged value in the capacitor or the initial current in the inductor. After having this particular arrangement, there is no external source. So, due to this absence, this particular characteristic is regarded as the free response characteristics, and the ultimate relationship is governed by the relation V of t is equal to V0 e to the power minus t upon tau for the RC circuit, where say the inductor current is I0 e to the power minus t upon tau for the RL circuit. The time constant, which is the RC for the RC circuits, and it is L upon R for the inductive circuits, is representing the physical characteristics of the system. Now we are in a position to start the discussion on the step response. So this situation arises when the DC source is suddenly applied. As an example here, the RC circuit is considered. Now the switch is closed at time t is equal to 0, which is giving rise to the current because of this external source Vs. We are presuming that the capacitor is initially charged to the level of voltage V0. This particular charging has been established because of the some other arrangement likewise in the circuit. But the focus is on the behavior after the switching, so that's why that particular is not shown here. As say the current is common, so it is resulting into the KVL relationship. Supply voltage is equal to the capacitor voltage plus the voltage drop across the resistor. This particular is giving rise to a differential equation of the first order dV upon dt plus V upon RC is equal to Vs upon RC. This differential equation terms are rearranged into the form likewise. So the voltage terms are appearing on the left hand side, the time term is appearing on the right hand side. This is integrated, it is giving rise to the general form V minus Vs is equal to A e to the power minus t upon Rc. This coefficient of integration A will be evaluated by the initial conditions. So when say we are applying the initial condition t is equal to 0, then this particular is giving rise to the evaluation of coefficient A as V0 minus Vs. So please be mindful that this V0 is the initial voltage, whereas Vs is the external source voltage that remains in the circuit for a long time. So because of this, there is a voltage expression which is suggesting V of t is equal to Vs plus V0 minus Vs e to the power minus t upon tau. As mentioned previously, the time constant is explained as tau is equal to Rc. So the complete response describing the behavior before the switching operation and after the switching operation is explained by the equation likewise. So what we are seeing on this particular graph, that with the initial voltage there is a exponential rise of the voltage ultimately attaining to the steady state level V of S. So as we are seeing that this particular component is represented into the two components, so natural response component and the transient or say the force response component. The force response component, which is the steady state value, so as available from this particular diagram, it is as approaching the steady state value of Vs. So that particular is clear, and the same relationship can be obtained while say we are substituting t is approaching to the infinity into this. Other component is the transient component, so it is expected to decay and vanish completely as the time t approaches to the infinity. Just to have a further arrangement, we are reiterating the term. So V0 was the initial voltage, so that particular is now regarded as the V0. The final voltage, which is the Vs, that particular is regarded as the V infinity. So the ultimate relationship is now explained with the help of final value and the initial values. So just to define the complete response, we need three parameters: initial voltage value, final voltage value, and the time constant. It is needless to mention that this time constant is depending on the resistance and the capacitance of the circuits, which are the physical parameters. So if suppose we are considering a case of initially relaxed capacitor or uncharged capacitor, then the initial voltage will be 0. That particular is substituted here in this expression. So the final expression is coming out to be Vs multiplied by 1 minus e to the power minus t upon tau. And the derivative is done to calculate the capacitor current, so that particular is also shown. For this initially relaxed capacitor, the response characteristics are plotted likewise. And say the time value is tau. This particular, the response value is now 632 of the Vs. Vs is the final value. So you can say the tau is the time needed or expended for the system to attain the voltage level of 63.2% of its final value. So this particular is a distinction. Here we are defining in terms of the final value, where in case of the free response it was defined in terms of the initial values. If suppose say you wish to write it with respect to the current, it can also be defined on the analogous line, because the current in this case is exponentially decreasing. Now ultimately, previously we considered the switching operation at time t is equal to 0. So instead of that, if suppose say the switching is affected at time t is equal to t0, so the equations are coming out to be changed because of the change in the voltage initial conditions. So now the initial condition will be V of t0 is equal to V0. So that particular is giving rise to the arrangement V of t is equal to V infinity plus V of t0 minus V infinity multiplied by e to the power minus t0 upon tau. So this negative sign which is appearing has to be accounted likewise. Now on the analogous line we can carry forward the discussion for the RL circuit. So again say we are considering that there will be a DC source continuously in the circuit after the initiation of the switching operation. So the behavior is represented likewise. Before that, the initial inductor was carrying the initial current of I0. So this is after the closing of the switch, the KVL relationship is Vs is equal to IR plus L di by dt. This equation is rearranged into the term, so we can do the integration likewise. So the current terms are on one side, the time terms on the other side likewise. It is giving rise to the equation I of t is equal to I, which is equal to the Vs upon R plus I0 minus Vs upon R multiplied by e to the power minus t upon tau. Now in this case, if suppose say that this DC source is impressed continuously, so as mentioned that the inductor will behave as a short circuit. So during that condition the current will be Vs upon R. So that is giving the I of infinity. I0 has been defined previously. So the final relationship which we will be getting, that I of t is equal to I infinity plus I0 minus I infinity into e to the power minus t upon tau. So in this particular case also, the current is explained with the help of three parameters: initial currents, final current I infinity, and the time constant. So the expression is coming out to be the analogous as we have obtained for the RC circuit. Only difference here is that in RC we are getting the expression for the capacitor voltage. Here say the expression for the inductor current is resulted. Now if the switching is affected at time t is equal to 0, the equation has to be modified accordingly. Now to define time constant, we can make a arrangement on the analogous line and consider the case of initially relaxed inductor. So initially relaxed inductor suggests I0 is equal to 0. The characteristic is plotted, so the current is exponentially increasing from 0 up to the I infinity level, which is Vs upon R. So on that particular basis you can define the time constant is the time expended to attain 63.2% of the final steady state current value. You can also define in terms of considering the tangents likewise. So if suppose say the current continue to increase with the initial rate of increase, then the final steady state value will be achieved in the time t is equal to tau. So likewise you can calculate. So in case of inductor or the RL circuit, you are expected to calculate or find out the expression of the current first, then calculate the inductor voltage, power, etc. Likewise. So as a summary, what we need? We need the three parameters, the I0, I infinity and the time constant for the RL circuit, whereas V0, V infinity and time constant for the RC circuit. So to calculate the initial values, we have to clearly represent the circuit before the switch operation. We have to assume that the circuit is operating in this stage for sufficient long time. So that means there will be no transients. Thereafter, you can represent the capacitor by the fully charged capacitor like an open circuit, or the inductor like a short circuit, and therefore calculate the capacitor voltage V0 or the current I0 as applicable in case of the RC or the RL circuits. Now thereafter we need the time constant tau, which is depending on the circuit parameters. So the circuit parameters is case basically is dictated by the R equivalent. We have considered only one passive element as such. However, the number of resistive elements can be different and so on. So you are requested to formulate Thevenin equivalent of the circuit with considering the reactive element as the load terminal. So with that consideration, you will be forming the equivalent, and whatever say the RTH calculated, that particular will be deciding the value of the time constant for both RC and the RL circuits. So for the RC it will be RTH into C. For the case of RL it will be L upon RTH. From this equivalent, when say we will be able to calculate the VTH, that particular will be the final value of the voltage for the RC circuit, whereas the I infinity, which is for the RL circuit, will be VTH upon RTH likewise, because the analysis has been carried out keeping the Thevenin equivalents in mind. Now with this background we can discuss few examples. So one example has been considered for the RC circuit, another for the RL circuit. Here we have to calculate the voltage, the capacitor current and the energy likewise. So this particular is a switching operation. As per the indicated diagram, the switch is closed at time t is equal to 0. So we are presuming that the switch is open before the operation for a sufficient long time. So that particular is giving rise to the first equivalent likewise. So with the supply voltage remaining effective for the sufficient long time, the capacitor will get fully charged. Because of this, the charge level will be equal to the battery supply voltage. There will be no current likewise. So the V0 is equal to 10 volt in this. On this basis, you will be able to calculate the WC0, the initial energy stored in the capacitor. Now after the switch operation, the circuit will be like this. Now we have to calculate the voltage across the capacitor. What we will be seeing that when say this particular circuit is remaining active for sufficient long time, it will be fully charged, and thereafter there will be no current in the capacitor. So when we are applying the nodal equation here, the expression will be like VOC minus 50 divided by 6, so that will be the direction of current, plus VOC minus 10 upon 2 is equal to 0. So in that way we will be able to get the value of VOC as 20 volt. Now this particular is getting open circuited. These two are the voltage sources. So to calculate the RTH, we need to short circuit the voltage source. So because of this, the 2 ohm and the 6 ohm resistances are coming out in parallel, that particular is giving rise to the RTH is equal to 1.5 ohm. So RTH is known, the capacitance value is already known, VTH is also known, so we can calculate the value of time constant, that is RTH into C, it is coming out to be 0.5 second. This V infinity will be equal to the 20 volt, likewise. So from this basis you will be able to find out the expression of the voltage, and this particular voltage, when allowed to be for sufficient long time, then ultimately it will be charging at a level of 20 volt. So the energy will be calculated likewise. The capacitor current you can calculate after calculating the voltage level C dV by dt. So that particular is coming out to be 20 e to the power minus 2t. Now the current is positive in this case, which is coming out to be different from the free response characteristic, because in this particular case the current is established by the external source. So that's why the current is coming out to be positive here. Now consider the another example for the RL circuit. Here say the switch is opened at time t is equal to 0. So before that the switch was closed, and we are interested in finding out the inductor current likewise. So when say the switch was closed, it is represented by a short circuit. Because of this short circuit, this 3 ohm resistance will be ineffective. So the circuit resistance will be now the 2 ohm. When say this particular source is remaining active for sufficient long time, the current through this inductor will be I0, which is 10 upon 2, 5 ampere. Initial energy you are able to calculate by half Li square. Now the switch is operated, or you can say the opened at time t is equal to 0. So because of this opening, 3 ohm resistance is coming out in series with the 2 ohm resistance, so the effective RTH will be 5 ohm. Because of this, time constant is calculated L upon RTH, which is 1 upon 15 seconds, and the I infinity will be decided by this particular voltage and the Thevenin equivalent resistance, so that is 10 upon 5 is equal to 2 ampere. The final current you are able to calculate it likewise, so that is giving rise to the 2 plus 5 minus 2 e to the power minus 15t, or you can say 2 plus 3 e to the power minus 15t. So as say the time will be progressing, this transient component will get vanished. The VL is coming out to be L di by dt. So they here what we are seeing, that the voltage is coming out to be negative. So the voltage negative is suggesting that the current level is decreasing in this particular example in comparison to the initial current I0. So having discussed these particular examples, now we can summarize the things for this particular step response arrangement. The step response characteristic is well defined by the initial value, final value, and the time constant. So these particular relationships are summarized here for the inductor current and the capacitor voltage. There is no change in the expression as such if we are making a correspondence between the inductor current and the capacitor voltage. The time constant can be defined as the time needed or expended for initially relaxed system to attain 63.2% of the final steady state value. Only thing which need to be cared, that we have to define the Thevenin equivalent carefully while considering the capacitance or the inductor as the output terminal. For further reading, you can go for this particular textbook. Thank you.